evening, everyone. Myself, Dr. Suparna Rudra, Assistant Professor, the Department of Chemistry, Brainware. So, for B.Tech course, spectroscopy is very important topic. So today, I shall discuss about electronic spectroscopy. So let's start. Now, what is spectroscopy? Spectroscopy is actually study of interaction between electromagnetic radiation and matter. Now, spectroscopy is very much useful for identification and characterization of molecules. You have already observed that when white light passes through a prism, it will be splitted into 7 different colors. So this is the part of spectroscopy. Now the splitting of light was first observed by Sir Isaac Newton. Now, what is electromagnetic radiation? Electromagnetic radiation means light and it travels in the form of waves. See that in this picture, this yellow line indicates the electric field and the blue line or blue wave indicates the magnetic field. So the electric field and magnetic field, two different waves, are in perpendicular to each other. Now, this is the propagation of light. The propagation of light direction is perpendicular with the magnetic field as well as electric field. Propagation of light is the direction of movement of light. Now, light or electromagnetic radiation, we can explain this light or electromagnetic radiation as wave. So this is a sine curve and it is plotted displacement versus distance. Now this is a sine curve. Y is the amplitude and the highest amplitude is known as crest and the lowest amplitude is known as trough. Now the distance between two crests is known as wavelength. So lambda is wavelength. Now one important formula is, we all know about it, E equal to h nu. What is E? E is the energy of the light. H is Planck's constant, which is 6.626 into 10 to the power minus 34 joule second. Nu is the frequency of light. Now nu is equal to c by lambda, where c is the speed of light, 3 into 10 to the power 8 meter per second. Lambda is the wavelength. Now from this formula, you can see that energy of light is directly proportional to the frequency of light, but it is inversely proportional to the wavelength of light. That means if the wavelength of light increases, the energy of the light decreases. Now, this is a picture of electromagnetic spectrum. You all know different kind of lights like cosmic rays, gamma rays, X-ray, UV visible rays, microwave, IR, radio wave, etc. As in the previous slide, you have seen energy is inversely proportional to the wavelength. So, in this picture, see at the right hand side, there are longer wavelength of light. So, microwave, radio wave, these are long wavelength. But high energy light like cosmic ray, gamma ray, X-ray, they have small wavelength. Now this is our visible range, wavelength nearly 400 to 800 nanometer, and the frequency range is 7 into 10 to the power 14 Hz to 4 into 10 to the power 14 Hz. Now, basic idea about the energy of the molecule. Now, what is energy of molecule? Energy of molecule means the total energy of translational energy as well as internal energy. Now, internal energy is summation of electronic energy, vibrational energy, rotational energy, and nuclear energy. Now, translational energy of a molecule is function of temperature, so that we will not consider it in spectroscopy. When electromagnetic radiation falls on a molecule, then molecule absorbs some amount of energy from the radiation and it becomes excited. And then it will move to a higher energy state from the lower energy state. Now, electronic spectroscopy or UV visible spectroscopy. This is the main topic. Now, as I have already said that when we irradiate a molecule with light, then the molecule will absorb some amount of energy, and the electrons present in the molecule will move from lower energy to higher energy orbital. Now, absorption of radiation in the ultraviolet and visible region causes promotion of electrons from lower energy sigma, pi and n molecular orbitals to vacant higher energy antibonding molecular orbitals. Antibonding molecular orbitals means pi star orbital, sigma star orbital, as you have already know this, because pi star, the star means antibonding orbital. So the electrons absorb energy and they will move from lower energy bonding orbitals to higher energy antibonding orbitals. This is a plot, extinction coefficient versus wavelength. Now, when we irradiate a sample with the help of light, then if we plot molar extinction coefficient versus wavelength, this is our plot, and you can see here near 500 nanometer the molecule absorb more light. That means the maximum wavelength here is lambda max. So lambda max is what? When molar absorptivity is plotted against wavelength, then absorbance becomes maximum at a particular wavelength. So at a particular wavelength, the molecule can absorb more energy. This wavelength is known as lambda max. Every compound has distinct lambda max value. Now, what are the probable electronic transitions? From the molecular orbital theory, you already know that there are different bonding molecular orbitals and antibonding molecular orbitals. In this picture, you can see the bonding molecular orbitals like sigma bonding, pi bonding and non-bonding. And the antibonding orbitals are pi star and sigma star. So there are different types of electronic transition may happen, like sigma to sigma star, sigma to pi star, pi to sigma star, n to sigma star, pi to pi star, n to star. Now, the energy gap between this sigma and sigma star is highest. Now, all of these transitions are not allowed transitions. So, the allowed transitions are sigma to sigma star and pi to pi star, where the symmetry of the orbitals are same. That means symmetry of sigma and symmetry of sigma star same, symmetry of pi and symmetry of pi star same. So these transitions are known as allowed transitions. Similarly, the forbidden transitions are n to pi star and n to sigma star. That means the symmetry is not similar. See the picture of UV visible spectrophotometer. Suppose this is the source of light. This is the source of light, and this is the cuvette present in the spectrophotometer where we can take our sample solution. This light is known as incident light. Now, this light, after absorbing some amount of light, this emitted light is known as, the rest of the light is known as transmitted light. This is the detector, and this is the computer for signal processing and output. Now, in this cuvette, we will take our sample solution, and this cuvette is made of quartz. It is called quartz cell, having dimension 1 centimeter into 1 centimeter, and we can choose our solvent like it should have high purity, it must not absorb radiation, must be chemically inert. So most of the solvent we have used water, ethanol and N-hexane. Now, what are the basic principles of UV visible spectroscopy? There is important principle or law, which is known as Lambert-Beer's law. Suppose this is our incident light. The intensity of incident light is known as I0. This is transmitted light, intensity is I. This is our sample solution present in the cuvette, and the length of the cuvette is L. Concentration of the solution is C molar. So, according to Lambert-Beer's law, the absorbance of monochromatic light is directly proportional to the path length and concentration of the solution. Now, monochromatic light means single wavelength light. Now, log I0 by I is equal to A. A means absorbance. This A is equal to epsilon Cl. What is epsilon? Epsilon is molar extinction coefficient. C is the concentration of the sample solution, and L is the path length. So this is our basic formula of UV visible spectroscopy. Electronic spectroscopy is also known as UV visible spectroscopy, as UV visible light is responsible for this spectroscopy. Now, what are chromophores? Chromophore means the presence of an isolated functional group which is not in conjugation with any other group said to be called a chromophore. They show characteristic absorption in UV visible spectra and thus reflect characteristic color. Suppose benzene having lambda max 210, 210 nanometer, and here naphthalene 220 nanometer, anthracene 250 nanometer, and so on. Next, oxochrome. What is oxochrome? Oxochrome means there are some groups of atoms which can alter the capacity of chromophore to reflect colors. They impart a particular color when attached to a chromophore, but when present alone, they will fail to produce any color. When attached to a chromophore, they can interact with it and cause a shifting in the absorption towards longer or maybe shorter wavelengths. So these are the oxochromes. Now what is bathochromic shift? So there may be two types of shift, bathochromic shift or red shift or blue shift. So what is bathochromic shift or red shift? Shifting of absorption maxima towards higher wavelength or longer wavelength is known as bathochromic shift. So as energy is inversely proportional to wavelength, so higher wavelength means lower energy. So there is an example. Suppose phenol is treated with alkali. What will happen? This proton will absorb by OH minus ion. So a phenoxide anion will form and the resonance will increase due to the availability of electron present in the oxygen. So as the resonance increases, the energy of the system decreases. That's why lambda max increases. So the shifting of lambda max from lower value to higher value is known as bathochromic shift or red shift. So when we add some amount of alkali into the phenolic solution, lambda max of this system will shift towards higher wavelength. Next, blue shift or hypsochromic shift. Blue shift means shifting of absorption maxima towards lower wavelength. Lower wavelength means higher energy. There is an example. Suppose aniline, there is a lone pair on nitrogen. If we treat this aniline with acid, it will form anilinium cation and resonance will decrease because the availability of this electron pair will decrease. So if resonance decreases, that means the energy of the system will increase. So the absorption maxima will shift towards lower wavelength, and this is called blue shift. Now, effect of conjugation in polyenes. As the conjugation increases, the movement of electron increases and the potential energy of the system will decrease, and as the energy of the system decreases, lambda max will shift in higher value. So we will see greater the conjugation, greater the lambda max value. For example, 1,3-butadiene, the lambda max value is 217 nanometer and 2,4-hexadiene 227 nanometer. Now steric effect. Suppose cis-stilbene and trans-stilbene. In the cis position, two phenyl groups are at the same site. So there may be some steric hindrance, and due to steric effect, the energy of the system will increase, and as the energy of the system increase, lambda max will decrease. So trans-stilbene has lesser energy than cis-stilbene because it is more stable. Trans-stilbene is more stable. So lambda max of this trans still being, as energy is lower here, lambda max is higher in case of trans still than the cis still. So therefore trans still being absorbs at longer wavelength than cis still being and has a higher lambda max value. There are huge applications of UV visible spectroscopy. It can be used in quantitative analysis of compounds, identification of organic, inorganic compounds, structural elucidation of the molecules, study of conjugation in organic compounds. It can be widely applied in pharmaceutical industries. It is very helpful in case of analysis of proteins and nucleic acids and monitoring chemical reactions, kinetics, etc. Now it is all about our UV visible spectroscopy or electronic spectroscopy. Thank you.